Hi, this is Mrs. Baston, and today we're going to talk about acid-base titrations, which is section 17.3. So if we first look at what a titration is and what it's used for, you can see the setup there. This is similar to what we did in class. So this is a technique where you use an acid or a base solution of known concentration is reacted with an acid or base of unknown concentration. The goal here is to figure out the molarity of a solution of either acid or base using a solution of known concentration of acid or base. So this particular one here is similar to the one we did in class. So you can see that you have a burette that contains a known concentration of NaOH, similar to the 0.1 molar NaOH that we used in class. And in the beaker below is a solution that is HCl that's an unknown concentration. So what you're doing is you're going to add the NaOH to the HCl in the beaker below until it reaches the equivalence point, which is when the amount of acid equals that of the base that you added. When it reaches the equivalence point, then you can use stoichiometry to figure out how many moles of acid you have in the beaker, and then using the original volume of acid, you can then calculate the molarity. So we're going to go through and look at a couple graphs here and just kind of talk through some of the differences in the graphs depending on whether you're using strong acids, weak acids, etc. Okay, so this first one we're going to look at is the titration of a strong acid with a strong base. So this is like the most recent titration that we did in class. So a couple of things to notice here. The first one is if you look at the initial pH, this is one way that you can tell that it is a strong acid, strong base, because notice the original pH is below 2, so it's in the range of about 1 or so. So you know from that you're starting with a strong acid, because that's where the pH probe is. It's in the beaker at the bottom. Then if you look at the shape of the graph, a strong acid, strong base titration has a pretty straight curve up here and then a very sharp jump when it hits the equivalence point, and then it flattens back out at the end. Okay, so we're going to look at how this compares to a weak acid, strong base titration, and how that graph is a little bit different, or that curve is a little bit different. So a pretty straight line here, straight line up, and then it flattens out at the top. So what's going on here is this original, this line down at the bottom is where you're slowly adding base and the pH is slowly increasing. As it gets close to the equivalence point in the middle here, if you remember that sometimes just one drop causes it to jump a huge pH difference. So the equivalence point is when they're equal molar amounts. And if you notice, if it's a strong acid, strong base titration, the equivalence point is at 7. Which is this right here. So it's neutral for strong acid, strong base. Then after that, you continue to add base, then it's going to increase in pH, and eventually the pH kind of levels out around 12 or so. So now let's compare this to, this is a strong base, strong acid. So this would be the opposite of what we just did. So in this situation, you would be using a known concentration of acid, and you would be adding it to an unknown concentration of base. So notice this time you're starting with a high pH because the pH meter is in the unknown base solution in the beaker, and you're slowly adding acid to it. Notice though you still have this very kind of straight, and then it flattens out, and then straight at the bottom. Similar, it's almost like you just reversed that previous curve. So this is still characteristic of a strong and strong. So this one's a strong base with a strong acid, but strong and strong, you're going to get this characteristic S shape. Notice also the equivalence point is still at 7, and that's going to be true of the strong base, strong acid. Okay, now when we look at a weak acid with a strong base, this is similar to the first titration we did, where you tried to figure out the concentration of either the 7-Up or the pickle juice or the aspirin solution, depending on which one of those you chose. So look at this one for a second. Let's look at some of the characteristics that show how this would be a little different than the strong and strong. The first thing to notice here is look at the original pH. So the original pH is around 3, instead of around 1 like the previous one. So that's your first clue that this is a weak acid with a strong base. The next thing to notice is if you look at this original little curve here before you hit the equivalence point, it's not as flat. It's a little more of a gradual curve. What's happening here, because you have a weak acid, there's a little bit of buffering going on. So you'll notice that this curve looks very similar to the curves that you saw when you did the titrations with the buffer. So it's a little more gradual change in pH because that change is being buffered because of the components of the weak acid. Next thing to notice is when you get to the equivalence point here, the equivalence point is greater than 7. So it's a little bit higher than 7, it's around 8 or so. So that's another characteristic of a weak acid strong base. And then after that, you see it kind of flattens back out, just like the other one did once you start adding the base past the equivalence point. So again, a couple characteristics here. The original pH is a little bit higher. That tells you it's a weak base. You've got a more gradual curve in the beginning because of some buffering that's happening, and then you have a pH above 7. So those are all things that show you that it's a weak acid strong base just from looking at the graph. Okay, the other thing you had to do here was you had to look at what indicator do you want to use. Now, you guys use the pH meter, so you didn't have to rely as heavily on the indicator. The indicator was just kind of, it helped you know about when the equivalence point was going to hit, but you had that nice pH meter that was calculating or that was recording the pH for you. If you don't have a pH meter, then you could use the indicator to let you know when you hit that equivalence point. So you have to pick an indicator that changes color near where the equivalence point is. So if we look at these two examples here, this first one is a weak base strong acid titration. So you're starting with a weak base. So you notice the pH is a little bit lower to start with. Also notice this is a little more gradual curve, just like the weak acid curve we just looked at. But for this one, the equivalence point is less than 7. And the other thing to notice, we were using phenolphthalein, which changes in this range here. Phenolphthalein would not work for this particular titration because it would change before you got anywhere close to where the equivalence point was. So if you look at this next graph over here, if you were doing this titration, you would want to choose, in this case, methyl red would be a good indicator because the methyl red changes around where that equivalence point is. So some of you got a chance to pick one when you were doing some of the buffer, with the buffer titrations where you picked a different indicator that changed, but you have to be careful with picking your indicator because you want to make sure you pick an indicator that changes color near the equivalence point. Okay, the last graph we want to look at is a titration of what's called a polyprotic acid. So we've been dealing with mainly monoprotic acids, so acids that only have one proton. Now some of you did do a titration with the citric acid, which is a polyprotic acid, but we didn't collect enough data to be able to see all of those, the curve like you see here. So what you're seeing here is when you titrate a polyprotic acid, you hit an equivalence point for each removal of an H. So the curve is going to look a little bit different. It's still that characteristic S curve, but you have several of them instead. So like on this one, you can see that when you start out, you have the H3PO4. When you hit this first equivalence point and one of those H's is removed, you hit the H2PO4. There's another equivalence point, you have H3PO3, H2PO3, and HPO3. So it's a little different curve. We're not going to deal as much with these, but just so you can see that if you have a polyprotic acid, the graph of that, the titration curve, is going to look a little bit different.